Okay, picture this. You're sitting in the examination hall. The clock on the wall is literally ticking down. The silence is deafening. And you flip to the next page of your Cambridge 0606 additional mathematics paper. And there it is, a massive, intimidating, simultaneous equation problem just staring back at you. For most students, right here, this is where the panic sets in. I want you to imagine two very typical students in this exact scenario. Let's call them Alex and Sam. Now, when Alex sees this problem, the approach is just pure brute force. We're talking overloading the page with raw mathematical facts, scribbling down literally every formula they can remember, but with absolutely zero analytical structure. It just becomes this messy block of numbers. Sam, on the other hand, Sam rushes. Sam spots a familiar variable, completely skips over reading the specific command words, jumps straight into solving, and ultimately misses the actual requirements of the question entirely. If we were to look at their papers side by side right now, we just see a sea of red pen marks crossing out all that hard work. But listen, there is a different way, a much better way. In today's explainer, we are going to look at these complex IGCSE simultaneous equations not as these terrifying mathematical roadblocks, but as uncarved blocks of raw marble. Mastering these equations is honestly exactly like being a master sculptor. It's all about systematically chipping away the irrelevant information to reveal the beautiful, flawless, final solution hidden inside. We are going to transform those red crosses into green check marks. So we really have to ask the central question, why do so many students drop marks on simultaneous equations? Like, why is this specific, recurring topic the downfall of so many brilliant Cambridge 0606 students? Well, the truth is, it's not because the fundamental algebra is impossible. It's actually because these questions are meticulously designed by Cambridge examiners to test your working memory, your formatting discipline, and your ability to juggle multiple logical constraints at the exact same time. You see, simultaneous equations in additional mathematics, they aren't just your basic linear x and y problems from lower years. They are complex hybrids. They weave together linear and nonlinear elements, demanding that you seamlessly transition between straight lines, quadratics, circles, and curves. When students fail here, it is rarely a failure of basic addition or subtraction. It is a failure of strategy. They get totally lost in the algebraic weeds, they forget what variable they were even solving for in the first place, or they find x but completely forget to substitute it back to find y. Basically, they lose track of the big picture. And that is exactly what we are going to fix today by shifting your mindset from that of a stressed-out student to that of a strategic sculptor. Okay, let's dive into this. Here is our mathematical roadmap for today. First, we'll cover the core principles. Second, we'll outline the procedural framework. And finally, we'll go through some crucial examiner warnings. Let's start with Section 1, Core Principles, Facing the Raw Marble. When you first look at the daunting equations presented on the exam paper, they look like this intimidating, uncarved block. Your initial instinct, kind of like our student Alex, might be to just start hacking away with random algebra. But a master sculptor, they study the marble first. You need to understand the grain, the faults, and the structure of the mathematics before you make a single mark on the page. Take a look at these examples taken directly from the Cambridge Additional Mathematics syllabus. These are your raw blocks of marble. Look at the first one, y minus x plus 3 equals 0, paired with x squared minus 3xy plus y squared plus 19 equals 0. Okay, this is a classic setup, a linear equation intersecting a nonlinear curve. The sculptor's first strike here is isolating y in the linear equation to get y equals x minus 3. Once you've done that, you carefully substitute it into that chaotic quadratic right below it. Now, look at the second pair. xy squared equals 4 and xy equals 3. Our friend Sam would probably try to isolate x into some messy fraction and plug it in, right? Which creates an absolute nightmare of rational functions. But a strategic student notices a structural shortcut. They see that xy squared is actually just xy multiplied by y. So if xy equals 3, then 3y equals 4. Instantly, the marble just falls away. And check out the third one. X over y plus 2y over x equals 4, paired with y equals x minus 2. I know, this looks terrifying with those algebraic fractions, but look closer at the structure. X over y and y over x. They are reciprocals. If you let a temporary dummy variable, let's call it u, equal x over y, the equation beautifully simplifies to u plus 2 over u equals 4. It's a simple hidden quadratic. This is the level of analytical thinking you need. By mastering these specific structures, you aren't just doing math. You are literally decoding the examiner's secret language. Notice the stark difference between these two approaches to learning mathematics. This is exactly why students like Alex and Sam get stuck. Superficial breadth is the failing approach. This means memorizing isolated math tricks without understanding the underlying logic. It's learning a specific step for a specific question, but the second Cambridge changes the command word from solve to show that, bam, the student freezes. On the flip side, connected conceptual understanding is the top scoring approach. The Cambridge syllabus explicitly states that top-performing candidates exhibit mastery of precise definitions, causal relationships, and integration across different syllabus areas. Top students don't just know how to substitute, they know why substitution preserves the truth of the system. To achieve this, top students actually use a variation of the Peel framework, point, evidence, explanation, link, but adapted for mathematics. Point, identify the mathematical principle, like substitution. Evidence, show the precise equation you are using. Explanation, execute the algebraic steps flawlessly. Link, tie the final coordinates back to the context of the question. You really have to understand the specific command words Cambridge uses. Evaluate requires a completely different structural approach than derive. Connected understanding means your brain instantly maps the command word to the exact mathematical procedure required. Moving on to Section 2, the procedural framework, chiseling the details. Okay, so we've studied the raw marble, we understand the core principles, and now it's time to establish the strict, systematic sequence required to execute the math perfectly under pressure. This framework is literally what separates a chaotic page of numbers from a beautifully structured, full-mark response. Consider this mandatory 5-step standardized sequence as your mathematical chisel. Step 1, identify key elements. Deconstruct the question. What part is linear? What is nonlinear? What are the constraints? Step 2, apply relevant principles. Select your analytical framework. Are you going to use substitution or elimination? If you see reciprocals, like x over y and y over x, are you using a dummy variable? Step 3, execute analysis with clear working. This is where you actually do the algebra. But please notice the phrase, clear working. This means using proper headings, perfectly aligning your equal signs, and showing every single logical leap. Step 4, verify results. Guys, this is absolutely crucial. Let's say you got x equals 5 and x equals -2. You need to plug them back into the original equation to check for reasonableness. Do they accidentally create a zero denominator? Step 5, present in appropriate format. Did the question specifically ask for coordinates? If so, your final answer absolutely must be in brackets, x, y. Imagine applying this to Alex and Sam. If they followed the exact 5 steps, their frantic, error-prone scribbling would instantly transform into a calm, logical progression of algebraic steps. And that brings us to a really crucial takeaway, summarized right here. The method mark strategy. Process over final answer. If there is literally one secret you take away from this entire explainer, let it be this one. Cambridge additional mathematics examiners heavily award marks for logical processing. They're actively looking for clear annotation, proper mathematical terminology, and a highly visible trail of your reasoning. Let me paint a picture for you. Imagine you have a massive 8-mark simultaneous equation question. You do 6 lines of absolutely brilliant, flawless algebra, but on the very last line, you have a brain freeze and accidentally write 2 + 3 = 6, so your final numerical answer is wrong. Do you get 0 marks for the whole question? No way, because you followed the procedural framework. The examiner can clearly see your logic. You will very likely walk away with 7 out of 8 marks purely because of method marks. Conversely, if you do all the math in your head or scribble it on some scrap piece of paper and just magically write down the final correct answer, you might only get 1 mark, or sometimes 0, because the examiner cannot verify your process. Remember, process is everything. Let's move to our final section, Section 3, Examiner Warnings, Polishing to Perfection. Now that we have our chisel and our framework in hand, we are going to dive directly into the confidential principal examiner reports. These are the actual documents where the people who grade your papers outline exactly what goes wrong every single year. Let's fire through the top 3 examination mistakes that absolutely ruin an otherwise perfect mathematical procedure. As we go through these, ask yourself which one you are most guilty of. Mistake number 1, confusing cause and effect. In simultaneous equations, this often looks like circular reasoning. A student will manipulate an equation, substitute it back into itself, and then confidently conclude that 0 = 0. They totally confused the logical progression of their own algebra. Mistake number 2, forgetting to check format and presentation. We just talked about this, but it happens all the time. You did all the hard work to find that x is 3 and y is 4. But the question asked for the coordinates of the points of intersection. If you don't write it out in brackets, you lose the final presentation mark. It is such a devastating way to lose a mark because you actually knew the math. Mistake number 3, providing answers not specific to the given context. Imagine the equation models the length of a geometric shape. You solve your quadratic, and you get lengths of 5 and -2. If you blindly write down both answers, the examiner will penalize you. A length literally cannot be negative. You have to reject the negative answer to show the examiner you actually understand the context of the problem. And that actually perfectly illustrates our next point. Take a look at this direct quote from the Principal Examiner Report. Candidates consistently confuse key terminology. Always define terms before using them in extended responses. Consider this a massive examiner alert. You might be thinking, come on, this is math, not an English essay. Why do I need to define terms? But think back to our adopted Peel framework. When a question asks you to show that the line is a tangent to the curve, you cannot just do simultaneous equations and stop. You have to explicitly state to the examiner, for a line to be a tangent, the discriminant of the resulting quadratic must equal 0. You have just defined the mathematical condition. Then, and only then, you show that b squared minus 4ac equals 0. If you just magically produce a 0 out of nowhere without stating the terminology or the rule, you are leaving marks on the table. You absolutely must connect your conceptual understanding to your procedural execution. Let's bring all of this together into a time management matrix. What you see here is the ultimate problem-solving timeline for tackling a complex 8 to 10 mark simultaneous equation question. Top candidates use this exact timeline to manage their stress and polish their final mathematical masterpiece. Minute 1, deconstruct. Listen, you are not writing equations yet. You are reading the command words, you are identifying the linear and nonlinear parts, you are deciding on your overall strategy. Minute 5, now you are in the thick of it. You are solving systematically. Your working is crystal clear, your equal signs are perfectly aligned, and you are securing those method marks line by line. Minute 9, you are evaluating. You're taking your final x and y values and plugging them back into the original equations to double-check everything. You are ensuring the format matches exactly what the question requested. Actually, I have a challenge for you right now. The very next time you do a past paper, set a timer. Give yourself exactly 60 seconds to just scan the data and extract the core trend before you even pick up your pen. It will completely change how you approach the math. So, we arrive at our final provocative question for today. I want you to honestly look at your own study habits. Are you just memorizing isolated steps like Alex, crossing your fingers and hoping the exam paper perfectly matches what you saw in your textbook? Or are you truly sculpting the solution, taking your connected conceptual knowledge and adapting it to whatever raw block of marble the examiner puts in front of you? To guarantee top marks, you really need to apply the 3 rules we've walked through today. First, command word decoding. Know exactly what the examiner is asking for. Second, Peel framework application. Structure your algebraic logic clearly so you guarantee those method marks. And third, the time management matrix. Deconstruct, solve, and evaluate. So before you open up your next past paper, ask yourself, are you just going to hack away randomly at the marble, or are you ready to sculpt a masterpiece?